Welcome. In this video, we're going to look more specifically at one analytical technique called mass spectrometry. We've talked about mass spectrometry before because it's commonly used to find the mass of individual atoms and the relative abundance of each isotope, and that's the information we've used to calculate weighted averages for each element. So you can also find the relative molecular mass of a compound, and the empirical formula can be found from compositional analysis, so then the molecular formula can be found as well using these two pieces of information. And the nice thing about knowing the molecular formula, then you can determine what we call IHD, or the hydrogen deficiency. So this technique will also provide clues about the molecular structure, because besides telling you how much of each isotope you have, it also fragments the molecule and can give you some information about the pieces that break off, so what kind of functional groups or substitutions might be on that particular molecule. So let's talk about the basic process. In a very simple form, electrons are shot at the sample to knock electrons off. So if X represents your molecule and you shoot electrons at it, eventually an electron gets knocked off, so you end up with 2 electrons for each electron shot, and you end up with this positive ion. So the collisions ionize the molecule to form a positive ion, but they may also break up or fragment the sample. Okay, so when you look at the spectra, the largest mass has to be your original sample, your ionized parent, because a fragment can't weigh more than the original. But then all the other pieces are going to be information about the structure, what kind of chunks broke off. Only neutral fragments are broken off and the ion is left behind. So if we take a look at that, here's some common ones. If you knock a CH3, a methyl group off, that should have a mass of 15. Whereas if you knock an OH minus group off, it's going to have a mass of 17. Water, H2O, would have a mass of 18. 28, you can see, is going to be either ethene there being knocked off, a CH2 double bonded to itself, or carbon double bonded to oxygen, so we need a little more information to know which one. And just like 29 could be a methyl and ethyl group, or it could be the aldehyde group, a CHO group. And then 31, CH3 with an oxygen single bonded to it, and then 45, the carboxylic acid group, or the carboxyl group, COOH. So those are the common ones, and IB expects you to recognize these fragment patterns, and it's really not that hard because there's really just 3 things we're looking at: carbon with the mass of 12, hydrogen with the mass of 1, and oxygen with the mass of 16. So do some math and figure out, what would add up to it. Like 15 can't have an oxygen in it because oxygen alone weighs 16. So it must have a carbon. It can't have 2 carbons, so that just leaves me CH3 for 15. So I won't worry so much about memorizing it as being able to rationalize what each number must be representing. So let's look at an example. Below is the mass spectrum for ethanol, CH3, CH2, OH. And so the peak with the largest mass is 46. It doesn't have the greatest abundance, but it's got the greatest mass. It's the peak with the greatest mass, so I know that's my parent atom with a mass of 46. And then if I look at 45, that's when 1 hydrogen has been knocked off. If I look at 31, that means a mass of 15 has been knocked off, which we said would have to be a CH3 group. So then that would leave me, if I think about it, if I've got the CH3 group knocked off, that would take 15, and then my CH2OH is going to leave me 12, 28. It's going to leave me a mass of 31. So that makes sense, and 31 and 15 adds back up to the 46. If I have 29, it's sometimes easier to think about what got knocked off. If I have 29, 17 got knocked off. So that could be a carbon, but then it would need 5 hydrogen, which is unlikely. So it must be the OH that got knocked off, taking 17 and leaving behind this mass of 29. So that's the analysis you do when you're looking at the abundance versus what they call the Z, or the mass to charge ratio. So let's look at another example on the next slide. A molecule with an empirical formula of CH2O has the simplified mass spectrum shown below. Deduce the molecular formula and possible structure of the compound. So the molecular formula is pretty easy because I can look at this and see that the molecular mass is 60. The empirical formula has a mass of 12 plus 2 plus 16. So that gives me a total of 30. So the actual mass is 60. The empirical formula says 30. So I know the parent ion must have a molecular formula of C2H4O2. So then if I find the difference in mass between the parent and fragments to help me come up with the possible structure, I have a mass of 45, which means 15 broke off. Well, if 15 broke off, that would be a CH3 group. So this is telling me it's a CH3 group. If a CH3 group broke off, that would leave me a CHO2 group for the 45. Because I'm looking at this molecular formula. If I take a CH3 off for the 15, I'm left with just one carbon, one hydrogen, but both oxygen. So I've got a pretty good idea that this must be a carboxylic acid with just two carbons. The OH here, so there's my COOH group. And then my methyl group here, the CH3 on this end. And then the 43, that just lets me know that I lost 17, a mass of 17. So that could have happened if this OH group was broken off. That would account for this being left behind with the mass of 43 and this having a mass of 17. So my molecular formula appears to be C2H4O2, and my possible structure seems to be this carboxylic acid, which would be ethanoic acid.